States of matter and state changes for GCSE, iGCSE and general chemistry.
Chemistry Explained are chemistry lessons designed for you to participate in. So make sure that you are writing notes and completing tasks on paper or on tablet. Move through the lesson at the pace that suits you. Skip ahead or move back as you wish. Most importantly, when prompted, pause the lesson, complete the task, but taking your time and thinking the problem through. Resume and check and correct your answers before moving on.
Here is an overview of the lesson. We'll start with particle theory, move on to the three states of matter, state symbols, state change and associated temperatures, interpreting heating and cooling curves, and then the properties of gases. If you are following AQA, EdXL, OCR, A or B, you should pay particular attention up to state change and temperature. iGCSE would include interpreting heating and cooling curves and the properties of gases. Kinetic particle theory. The central idea is that all matter is composed of particles. These particles are thought of as very small, solid spheres in constant motion. There are no attractions between the particles in particle theory. Particle theory, as stated on the previous slide, has a number of simple limitations which you are expected to know about. Matter particles are not spheres. They are not solid. And there are attractions between those particles, and those attractions differ depending on the particles involved. Therefore, particle theory, although remaining useful as an explanation, is only partially accurate. So we will move on to the three states of matter. The three states of matter are, of course, solid, liquid, and gas. But let's consider firstly the arrangement of particles in those three states. So here we have state A, state B, and state C. What is the wording using kinetic theory to describe the arrangement of particles in the solid? Let's look at an example. We would say in the solid we have regular arrangement and very close, the particles are very close together. Using that sort of analysis, describe the particles in a liquid and describe the particles in a gas. Pause, write down your statements, come back to check against mine. Okay, so here we have B, a liquid. We would say that we have an irregular arrangement and that the particles are close together. In the gas, we would say we have a random arrangement and crucially the particles are far apart. Now let's consider the three states in terms of the motions of the particles and the attractions of the particles or between the particles. So we've got solid, liquid, gas. Write down some statements about the motion of the particles in a solid and the attractions between those particles for a solid, for a liquid, and for a gas. Pause the lesson. Come back when you have completed that task. Okay, so I'm going to say about the solid that we've got strong attractions. We've got vibrations only, by which we mean the particle is moving up and down, but returning to the original position, moving to the right, but then moving back to the original position, moving to the left, and moving back to the original position. So that is what is meant by vibration. In a liquid, we've got weak attractions between the particles in liquids, and they are relatively free to move. In a gas, the attractions between particles are very weak, and the particles show rapid free movement. Moving on to state symbols. State symbols are sometimes added to the substances in a chemical equation. So we have solid, liquid, gas. Pause. Can you recall the symbols that are used in chemical equations to indicate the state solid, liquid, and gas? Come back, restart when you have your answer. Okay, so bracketed S for solid, bracketed L for liquid, bracketed G for gas, but there is a fourth state symbol. Can you recall it? And can you explain its use? Pause, come back when you have done so. The fourth state symbol describes a situation where we have a solid solute, water as the solvent, and that solute dissolves in water to form an aqueous solution. Pause and write down the symbol added to equations to describe that situation. Okay, so we use the symbol bracketed AQ. You can see where it comes from, aqueous, the AQ. Let me give you a problem. Add state symbols to the balanced formulae equation for the reaction described. Small solid pieces of calcium carbonate react with a dilute solution of hydrochloric acid to form carbon dioxide gas, a solution of calcium chloride, and water. So here is the symbol equation, or the balanced formulae equation. Could you add state symbols to that? Pause, come back to check against my answer. Okay, so to reveal, calcium carbonate is a solid, hydrochloric acid was a dilute solution, calcium chloride formed a solution, carbon dioxide was a gas, and water is written as a liquid. Now let's talk about state change and specific temperature points. So let's name specific state changes. Solid to liquid, liquid to gas, gas to liquid, and liquid to solid. Pause, write down the names, come back when you're ready. Solid to liquid is melting. Liquid to gas, evaporation, or a special case of evaporation, boiling. Gas to liquid is condensing. And liquid to solid is freezing. Now these occur at particular temperature points. Can you name them? Pause, come back to check against mine. So to reveal, evaporation and boiling occur at the boiling point, but so does condensing. Those two opposite or reverse processes occur at the same temperature, the boiling point. Melting and freezing occur at the same temperature, the melting point. You may see the melting point, otherwise known as the freezing point. You may see the boiling point, otherwise labelled as the condensation point. Both of those labels will be used in GCSE. Let's look at state change temperatures, by which we mean melting point or melting temperature, boiling point, boiling temperature. You are expected to recall those temperatures, those temperature points for water. Pause, write down the melting point and boiling point of water. Okay. The melting point of water is 0 degrees Celsius and the boiling point is 100 degrees Celsius. You are expected to recall that at GCSE. But what is the state of water at 45 Celsius? Let's have a look at how we can deal with that problem. The first thing is to draw a number line, and then we know that above 100, water is a gas, and below 0, its melting point, it will be a solid, and in between, of course, it is a liquid. So now we just need to know where is 45 on that number line. Well, 45 is around about here, approximately. That's in the section that corresponds to water as a liquid. So what is the state of water at -5? Pause, come up with your answer. Okay, so water, of course, at -5 is in the section that corresponds to a solid. That's straightforward for water because you're very familiar with it. Let's try a problem on sulfur. Sulfur has a melting point of 119 and a boiling point of 445. What is the state of sulfur at 100 degrees Celsius? Pause, come up with your answer. Okay, so my solution is based on at 445, above 445, sulfur is a gas, and below 119, it's a solid. In between, of course, it is a liquid. Where is 100 on that scale? So 100 is here. This is 119. So 100 is below there. So at 100 degrees Celsius, sulfur is a solid. What is the state of sulfur at 400? Pause, come up with your answer. Okay, so at 400, it's in the section, that temperature corresponds to the section that has sulfur as a liquid. The state change temperature depends on the strength of the forces between the particles, not within any particles or molecules, but between the particles. So we start with a solid. Of course, the particles are close together. The change to a liquid, the particles become further apart. So it must be true that the forces between the particles have been broken or partially broken. That requires an input of energy. To break bonds, you put energy in. If the forces between the particles are strong, that will result in a high melting point. So the stronger the forces between the particles, the higher the melting point. Pause the lesson. Can you write equivalent statements using the correct terminology expected at GCSE for the change liquid to gas? Pause, come back when you've completed the task. Okay, so of course, the particles are spread out in a gas or far apart. That means the forces between the particles have been broken or overcome. That, of course, requires an energy input. The stronger the forces between the particles, the higher the boiling point. Liquid to gas boiling, so the higher the boiling point. Interpreting heating and cooling curves. So, interpreting heating and cooling curves. Stearic acid is mentioned in the specification. If we heat it up and monitor its temperature against time, we find that there are plateaux in that heating curve. That is, the temperature remains constant although the substance is being heated, and we equate that to a state change. The lower plateau, of course, corresponds to melting and occurs at the melting point. The higher plateau corresponds to boiling, and at a temperature that is the boiling point. So above the higher plateau, we have at temperatures above that higher plateau, the substance is a gas. Below the lower plateau, the substance is a solid, and obviously in between it is a liquid. So here is a cooling curve for a substance such as water. Hot steam is cooled and its temperature monitored against time. Pause the lesson and interpret this plot in the same way as I interpreted the heating curve on the previous slide. Take your time, put in as much detail as you can. Come back to check against mine when you are ready. Okay, so of course the fall in temperature forms plateau, and the plateau corresponds to state changes. The first state change will be from gas to liquid, which is condensing, and that occurs at the boiling point. The lower plateau will be freezing, liquid to solid, and of course that occurs at the melting point. The properties of gases, including diffusion. The volume of a gas is affected by pressure change. So here is a gas. We have the particles randomly spread out, of course, and let's assume that this is a low pressure. A piston is pushing down on the gas and controlling its volume. We have an initial low pressure. What would happen to that volume if the pressure is increased? Pause and draw your diagram. Okay, so my diagram would look like this. At a higher pressure, the volume would be decreased. The particles would be closer together. So two observations. At a higher pressure, the volume decreases and the particles are closer together. The particles do not change size or shape themselves. It's the distances apart that is affected by the change in pressure. So the volume decreases because the particles are closer together. Okay, so if there's a decrease in pressure, can you write similar descriptors using the same ideas? Pause, come back when you've done that task. Okay, so the sort of descriptors at GCSE would be, and if you decrease the pressure, so we move to a low or lower pressure, the gas volume increases, the particles are further apart. The particles themselves have not changed, but the distances between them have been affected by the pressure. The particles are further apart. The volume of a gas is also affected by temperature change. So if we take the same arrangement, we have a piston and a volume of gas at a certain temperature. What would happen to the volume if the temperature was increased? Pause, draw a diagram to represent the change. Okay, so my diagram, at a higher temperature, shall we say 50, whatever, the volume increases. The particles have more kinetic energy and move further apart. Can you write similar descriptors to describe the change when there is a decrease in temperature? Pause, come back to check against mine. Okay, so to restart, the volume, of course, if you decrease the temperature, the volume decreases, the particles have less kinetic energy and move closer together. Small additional point, this is of course at constant pressure. Gases and liquids also exhibit diffusion. Diffusion is a process by which substances at high concentration will move to regions where they are at lower concentration. So for instance, if there's a gas leak in the chemistry lab, you can smell it in one corner of the lab, but at the far corner of the laboratory, you can't smell the gas leak. However, over time, the concentration of particles will become even across the total volume. So we've moved from having high concentration in one region and low concentration in another into having an even concentration across the whole volume. That, of course, is explained by the free random movement of the particles in a gas or indeed in a liquid. So random movement without attractions between the particles results over time in an even concentration across the volume. The rate of diffusion depends on the molecular mass of a gas, or the relative molecular mass of a gas. You may have seen in the school laboratory some beads soaked in concentrated hydrochloric acid, which release hydrogen chloride vapor. At the opposite end of a reaction tube, we have beads soaked in concentrated ammonia, which releases gaseous ammonia. As time goes on, we see a reaction between hydrochloric acid and ammonia forming ammonium chloride, but that does not occur in the center of the tube for the simple reason that ammonia has a lower molecular mass than hydrogen chloride and therefore moves faster. Hydrogen chloride with the higher molecular mass moves more slowly. So hydrogen 1, chlorine 35.5 comes to 36.5 for the relative molecular mass. Ammonia, nitrogen 14, hydrogen times 3 is 3, so it comes to 17. Ammonia with the smaller relative molecular mass will move faster. Hydrogen chloride with the greater molecular mass will move more slowly, so the reaction between the two occurs. You see a white smoke of ammonium chloride, which is actually a solid held in suspension in air, and that will occur closer to the hydrogen chloride than to the ammonia, because ammonia diffuses more quickly than hydrogen chloride. As always, I recommend you look in your textbook at the end of chapter questions. Generally, there will be some practice questions and some past exam paper questions. Do try those, check your answers, and then move on to stores of past paper questions which are available online at websites, for instance, Physics and Maths Tutor. But of course, there are other websites that are equally as good.